house, Gauthier, Gidel from Milan, University of Montreal. Take it away.
Hello, everyone. Thank you, Costis, for the nice introduction. And thank you to the organizer of this workshop and of this semester assignments to give me the opportunity to present today. Today I'm going to talk about going beyond min-max optimization, and in particular, taking into account the learning dynamics in adversarial learning. And I'm going to focus on two specific aspects. So in the context of GANs, I'm going to focus about the implicit bias of Adam for GAN training, which is basically the goal is going to be to go beyond min-max optimization by considering the fine-grained dynamics of the optimizers. And then there is going to be a second part about going beyond min-max optimization by replacing the inner optimization methods by a sampling, the inner optimization loop, sorry, by sampling. And it's going to be in the context of adversarial training. Okay. So the first part is inspired by a joint work with Sami, Arthur, and Wangzi. And it's about the implicit bias of Adam for GAN training. So I think if you're here, you know what a GAN is. So I won't get into the details of this. I trust you. And basically what we care about is that this GAN is a game between two players, the generator and the discriminator, where the discriminator basically wants to maximize this, like basically the minus cross entropy, while the generator aims at minimizing this pair. And interestingly, yesterday, I think, we talked a lot about hidden convex-concave payoff. And the interesting point to notice is that the payoff of GAN is actually hiddenly convex-concave. So if you consider it, this payoff as a payoff of the function of the discriminator and the distribution of the generator, it's linear for the generator because it's just on the expectation here. And it's concave because the log is concave. Unfortunately, because it's too high dimensional, I mean, we cannot solve this min-max, even though it's convex-concave in the infinite dimensional space. What we do, as always, the solution is to parameterize our network. So we parameterize the classifier, our discriminator phi, and the generator phi. And we end up with a min-max problem that is now, unfortunately, is finite dimensional, but unfortunately, non-convex, non-concave. And so how do we solve this? How people have solved this in practice? Basically, at the beginning, at least, they solved it the deep learning way. So they just computed the stochastic gradient for theta, update theta with their favorite optimizer, compute the stochastic gradient for omega, update omega, and so on, and repeat. And the two things I want to, the main thing I want to focus on today is this idea of like, you have to pick an optimizer. And there is a huge discrepancy between when you use, for instance, standard stochastic gradient descent and when you use other optimizer such as Adam. Before that, maybe just a small parenthesis. People use stochastic gradient descent, but we all know, and we have seen a lot today, that it doesn't work. If we take the, I mean, in general, if we take the simple bilinear game, stochastic and even not stochastic, gradient descent ascent diverge geometrically away from the solution. So that's why there has been a huge line of work of people trying to propose new principled methods for GANs in the context of GANs. So all these works got inspired from the way older literature than this. So for instance, Costis has a paper on like optimistic methods for GANs, and optimism dates from 1960, no? Something like this, 80, yeah. And extra gradient dates from like Korpevelevich, 1979. So yeah, but this paper was kind of like revamping the old methods in the context of GANs. But unfortunately, there is an inconvenient truth, which is that at least personally, when I try to run these experiments on GANs, what I saw is this significant gap between stochastic gradient descent ascent and Adam. So this is basically the FID, threshold inception distance. Lower is better. This is what matters here. And on 4 different data sets, I had tuned the hyperparameters, so the basically learning rates, most of it, for stochastic gradient descent ascent and Adam for the ascent and descent direction. And I couldn't like get rid of this huge gap between the performance of Adam and SGDA. And that's a problem because when I tried then to use the principal methods that I proposed in the past, so for instance, stochastic extra gradient, when I tried to apply stochastic extra gradient to GAN training, what really happened is like I could improve SGDA, but I couldn't close the gap between the performance of SGDA and the performance of Adam in this context of image dataset.
What kind of tuning did you try?
I was tuning the learning rates of like both the gradient ascent and gradient descent step.
Clipping and
I
like standard gradient clipping and learning rate schedule.
I tried the learning rate schedule. I'm not sure I tried the clipping.
Because in BERT, also it's a common claim that you have to use Adam, but that's recently disproved.
Okay. I want to disprove it too. That's my goal today. So I agree that like my goal today is to try to address this practical gap and to figure out why Adam is working that well. And beyond the anecdotes, because it's my personal history, I want to show you like some facts that you know are more like about the community. If you look at the state of the art in image generation from basically 2017 to almost 2020, it was all GANs. After this, it was a diffusion model, so it doesn't work anymore. But if you look at all the SOTA GANs that has been released, all of them, I checked, all of them were using Adam as an optimizer. Also, if you look at all these, yes. Sorry. So y-axis is the FID. So the state of the art is always decreasing as a function of time. X-axis is the time. And so there is the WGAN GP paper, spectral normalization, big GAN, for instance, and some other improvements on the CIFAR 10 dataset.
So they use Adam, but
they changed the formulation of the GAN, they improved the architecture. But in terms of optimizer, it always has been Adam that was used for that training. And if you look at the papers that who proposed, let's say, principal methods such as optimism or anchoring, like all these papers, when they were trying to do some experiments on CIFAR, also plugged Adam on top of their techniques. And yeah, I'm part of this. And so the question I want to answer today is really like, why does Adam, what does Adam do that SGD does not? So very like a quick, basically reminder of what Adam is. So basically we have this update where we have the step size. So we update theta t by using a specific vector with like a step size. MT is basically a momentum, and we have a coordinate-wise renormalization that depends on the squared value of the passed gradient. So yeah, it's what's called an adaptive methods, and there is many justification to explain why it works well in practice, but this is not what I want to focus on, because all these explanations are in the context of minimization, and what I want to deal with is the context of min-max. Moreover, in the context of minimization, as mentioned a bit earlier, there is some work that are trying to argue that Adam can be replaced. For instance, in the context of image classification, there is this very nice oral presentation at NeurIPS 2017 that basically detail how a well-tuned SGD can outperform Adam. And there is the best paper award at iClear 2018 that basically showed that there was a mistake in the convergence proof of Adam. So if we want to use principal methods, we may not want to use Adam on top of it because then we break all the conversions. So yeah, so what we're going to to do is to try to deconstruct Adam in order to figure out what it has, what it does, what is the specific thing it does during the training. So basically, it's just an update vector that has a direction and a norm that differs from its SGD. Nothing crazy here. But so the crazy thing we tried is to try to disentangle the effect of the direction and the effect of the norm in the training. So we proposed two methods that we call ADA-LR and ADA-DIR, which basically corresponds to one of the optimizer use the norm of the Adam optimizer. You compute in parallel the SGD update and the Adam update. And for one, you use the norm of Adam and the direction of SGD. So you take your SGD update and you divide by its norm and multiply by the norm of Adam. And you do the same for the other player. And conversely, ADA-DIR, you take the direction of Adam and you multiply by the norm of SGD. So now what we have is like two methods. One follow the norm of Adam and the other one, follow the direction of Adam and the other one follow the direction of SGD. And experimentally, that's pretty interesting. What we get is that the one that doesn't follow the direction of Adam, so it follows the direction of SGD, but has the same norm as Adam, is matching almost perfectly and within error bar, outperforming Adam. So basically what it says is what we only care about, the first takeaway from this experiment, is that it seems that it's only the norm of the Adam vector, of the Adam update, that helps in performance. The second thing we noticed experimentally is that actually the norm of this vector was constant across time. So if we summarize this, the method that was working almost as well as Adam was this one, with the direction of SGD that was normalized and the norm of Adam. But if the norm of Adam is constant, we end up with this very simple optimizer that is basically normalized SGD. And so our hypothesis is that this optimizer should work as well as Adam. And this is just normalized SGD. So this is the thing we tried. We took the previous plot that was a bit unfortunate, and we added now some just layer-wise normalized SGDA and normalized SGDA where we normalize across all the parameters, sorry. And what we get is we are able within error bar to match the performance of Adam by just using this mini batch normalization step. So the conclusion experimentally is that normalized SGD is a proxy for Adam, or actually I prefer the Adam is a proxy for normalized SGD, and this can be an explanation of why it works well for GANs. Yes.
So your experiment is for GDA, right?
Yes.
Yes. We can do the same thing for regular minimization, right?
Well, sorry.
Minimization, just
yes.
Minimization. Do we have the same behavior that LR? What was the name of the tool?
Oh yeah, and normalized SGDA.
Is it still better in the regular minimization?
So that's a good question. We haven't tried in the minimization, but in minimization you can already outperform Adam with SGD. So in
but
some
between
sense,
these two algorithms.
Sorry.
But between the two algorithms that you have.
Yes. Also, something to notice that I don't talk about in the talk is in the context of GANs, people use Adam with some specific hyperparameters that are different from the one in minimization. In particular, they put no momentum and change a bit the beta 2. That is probably changing the behavior of Adam. So I don't think, and I think that's the point of this talk, I think Adam in the context of GANs does something very different than what it does in the context of standard minimization.
So just to be sure, in min-max minimization, they add or they are not adding?
No momentum in min-max.
No.
Sorry, is there any the hyperparameters that arise out of your hyperparameter tuning? Do you see any negative momentum, positive momentum, and the step size are equal, different?
Yes. So for Adam, it's 0 momentum. That is most of the time like the best at the rise. And it's always like a 2 time scale step size, so different step size for the generator and discriminator. I don't remember exactly which one is larger than which. And I think for normalized SGD, you need, I'm gonna say mistake. I think maybe, no, I don't remember if it's larger, but it's different from, your step size has to be different. Basically, it makes sense from this slide because this guy is just like plugged into the step size. So the step size of Adam is, when you tune, is very different from the step size of what you normalize SGD. Probably larger. You should get larger step size for normalized SGD, but I'm not 100% sure. So yeah, as an experimental conclusion, we have that Adam is a proxy for normalized SGD. And okay, why is it so great? First of all, I'm very happy because it's way much more principled. And why is it? Why do we care? Because now we can try to analyze and understand what normalized SGD does in the context of GANs. What is its implicit bias, and it's also way easier to tune. And there is the room for improvement. Now, if we have like extra gradient, it's way easier to try to analyze normalized extra gradient than to try to analyze extra Adam or optimistic Adam. So yeah, I feel like it kind of opens the room for a lot of like analysis and understanding. And so what we did is a preliminary analysis of the comparison of normalized SGDA versus SGDA in the context of a GAN that is already quite challenging. So we had a linear generator where basically what you want to learn is the weight VI. And so ZI are sample or binary latent variables that are basically sparse, non-negative, and non-positively correlated. So this is basically like what is summarized here. And you want to learn basically the weights here. And the distribution that is the target is just a mixture of 2 modes, U1 and U2, that are positively correlated. And basically your distribution is either, you can get your random variable is either U1, the realization, sorry, of your random variable, or either U1 or U2. So basically what you would like to learn with VI is these 2 vectors, U1 and U2, and you would like to learn the right weights. So for basically that depends on these 2 random variables S1 and S2. Interestingly, there is this work by Allen Su and Lee that argues that these ZI that are sparse, non-negative, and non-positively correlated can be seen as the distribution of the hidden layers of deeper neural nets. So this is what they kind of show in their analysis, that this is how like basically deeper hidden layers behave.
Did they prove that?
I think they prove like some like in this vein result.
This is like a sparse coding model, right? I understand.
It's basically, yeah, so the ZI are like
Bernoulli, what's it called? Bernoulli sparse coding.
yeah, but like, yeah, I mean, it's basically like they are sparse. Most of the time you have only 1 ZI, but you can have like very unlikely 2 ZIs. And so what we have in order to make it interesting is a two-layer neural nets with basically a cubic non-linearity. So it's cubic around 0, and then it's going to be linear at some point, just to deal with the Lipschitzness. We don't want the Lipschitzness of the discriminator to go to +infinity. But yeah, it's roughly a cubic discriminator, and we want to basically study the min-max, this min-max objective. And the 2 results we were able to show are the following. So basically, the first result is that for SGDA, for any step size choice that is constant, SGDA suffer from like mode collapse, precisely that like we can only learn the direction U1 plus U2. So you're never able to learn with your generator, with the weights VI, either U1 or U2, you're only able to learn the sum, which is like, I mean, the average of the mean of the distribution in some sense, something proportional to the mean of the distribution. So this is kind of the statement that is like a bit more detailed. And this is with like high probability. But yeah, the spirit of the statement is that we are not able to learn the right node. And basically, if we look at what like some illustration, what happens is like the discriminator in any case is because of the cubic nonlinearities is learning this direction, the direction of U1 plus U2. And once like the weights of the generator start to catch up, it's too late, and they only basically get the direction U1 plus U2. So here is like U1, here is U2. In green, this is the decision boundary of the discriminator. And something to notice in GANs is that the generator only gets signal from the discriminator. So the only signal that these data points will get is comes from the decision boundary of the discriminator. And so if the decision boundary of the discriminator has converged to something that is linear and directed by U1 plus U2, you cannot learn anything else. And that's kind of the spirit, like the spirit of the proof. On the other side, if you have picked the correct choice for normalized SGDA, you will learn the direction of both modes. So with the right, with enough iteration and enough steps, I mean the right step size tuning, what we were able to prove is that the generator is able to learn the direction of both modes, meaning that like there is a non-vanishing probability that basically we are close. We are close. There is a non-vanishing mass of the generated distribution that is close to U1 and U2. So the remarks here is like this is proven in a very specific setting that is not as general as non-convex, non-concave GANs and any architecture. It's for a specific choice of generator and discriminator, and it's only about the direction. So one very weakness of our analysis is that we are not able to learn the correct UI, but we are able to only learn their correct direction. So we need to renormalize to get the result. Also, we have no guarantees that normalized SGD learns the correct weighting, meaning that we have no guarantees that this probability is actually equals to the correct correct weights. So like because the target distribution is a mixture of U1 and U2, and there is no guarantee we recover the correct mixture coefficients. So the illustration is the following. So because of the normalization of the gradient, the generator is able to basically learn very quickly something. And what ends up happening in this experiment is that, as we can see, some of the mass goes on one mode and some of the mass goes on the other one. Of course, our theory cannot, I mean, we don't prove that all the mass is like on both modes, but at least we get a non-zero one on each of them. So the conclusion of the first part is that GANs has some, in some sense, very bad approximate stationary point and local equilibrium. And it seems that like normalized gradient could be one of the key for training GANs. And Adam, in some sense, was used as a proxy for normalized gradient, normalized SGD. And so in some sense, if we want to study minimax optimization, and in particular convergence in the context of learning, sometimes convergence guarantees are not enough because we have this like very bad like stationary point. And so we need to consider the dynamics of our optimizer. And in particular, like what is called, like what I call here, and like what people like to call implicit biases of each learning algorithm is important. But in that specific setting, it's really about understanding the fine-grained, having a fine-grained understanding of the dynamics. Really like figuring out in the context of GANs, what is going on and why normalized gradient does something that SGDA doesn't. So in some sense, and if we want to do this, of course, like general non-convex, non-concave minimax optimization is too general. So like the questions that remains open, I mean, of course, our analysis is in the case of batch of size 1. But more interestingly, can we extend this result to like more complex generator and discriminator and understand this like in the general setting of GANs? Maybe we could have a stronger result in that case where we don't only learn the directions. And can we extend this idea to other like multi-agent settings? Sorry about that. Such as multi-agent, for instance, reinforcement learning. Okay, so that concludes the first part of my talk. And now I have, I think, 15 minutes for the second part, which is exactly what I need to talk about like basically a distributional robustness perspective on adversarial training, where I basically want to go beyond this like min-max optimization by replacing the max inner optimization by some sampling. So in that work, we are in the context of adversarial examples. So very quickly, what is an adversarial example? There is this very nice and quote by Alexander Madry that says that machine learning is amazing. It's a wonderful technology because it can make pigs fly. And how do you do this? You take a picture of pig, you take your favorite classifier that classifies this picture as a pig, you add this imperceptible transformation that depends on the classifier that is called adversarial examples, and you get these new pictures classified with a 99% accuracy as an airline. Now, our goal in this work and in like basically the robustness literature is to have like robust classifier, meaning that we don't want to have flying pigs. So we want to train basically a model that will be robust against this perturbation. And one of the ideas to do this is to do what is called adversarial training, meaning that you train your model against these adversarial examples. And so the point I want to make today is, okay, but when we look at this inner maximization, what we do is like we look at the X tilde that doesn't come from the data distribution anymore. So in some sense, what the classifier sees is a new distribution that is a perturbed version of the data distribution. And so the way we may want to reformulate this maximization is by a maximization with respect to the distribution. And the question here is like, what is the P that we should set in order to have this equality between these two? To basically have the adversarial training formulation. So for a general P, this is called like distributional robustness, and I think we're going to have a very nice talk about this right after me. It's a very old field that starts before 2000, and that there is some people that recently draw connections with adversarial examples. I'm not the first one to notice that we can have basically there is a connection between these two formulations. Yes.
Just to be sure that I understand, it's the first time that I see that break. You claim that I have an integral, this is what I see. I have an integral and I have a maximum operator over a function. I can put out the maximum operator.
If you put the right constraint here.
I see. And the P would be a convex.
In that case, it will.
Okay.
Yes. That's the whole point. Actually, the P, I can do you the spoiler there. The spoiler, P is the Wasserstein ball. It's like the infinite Wasserstein ball of size epsilon around the data distribution, centered at the data distribution.
Interesting.
But it's a very good question because the next slide is giving you the details about this. So the novelty here is really trying to figure out what is the right P. So really making this tight connection about when, like, what is the P to get this equality. And basically what we figured out is that there is a connection between optimal transport and infinite Wasserstein ball constraint. So in some sense, you can see X tilde as the result of a transportation of X by following this constraint epsilon. And so in some sense, the p-adv, the intuition, is that it shouldn't be transported more than epsilon with respect to a certain metric. So yeah, so the way we prove this is like if we want to transport x tilde not too far from x, so we want a transportation map that transports the data distribution to the adversarial distribution with the constraint that basically, so we have this like transportation map that says who is transported to who, and what we want as a constraint in order to satisfy the blue constraint is that the support is only constituted of the y's here that are the same and x tilde that are smaller than epsilon with respect to this L infinity norm. So once we have this, we can realize that actually this exactly corresponds to what is called the infinite Wasserstein distance. So it's basically the infinite Wasserstein distance with respect to the L infinity norm. And what we got at the end is this very nice equality between adversarial robustness, adversarial training and basically distributional robustness with respect to this ball. Okay, but why do we want to do this? Because now we have this perspective that the adversarial distribution is just the result of a transportation of the original data distribution. And optimal transport has some very nice tool and tricks with regard to adversarial transport. And in particular, something very convenient often is to use the entropic regularizer in order to, when you do transport between two distributions. And so if we do this, if we add an entropic regularizer to our original problem, now we get a closed form solution for the optimal adversarial distribution. So basically, when we solve this maximization with an entropic regularizer, we get a closed form that is basically this one. What it says roughly is that the density at a adversarial example is proportional to exponential lambda, the value of the loss. So the higher the value of the loss is, the more likely the higher the density of the adversarial distribution is at the point. So it makes sense. The problem is, of course, it's harder to compute the normalization of this density, but we can basically simulate this distribution using Langevin Monte Carlo sampling. And so what we do now, because we have this closed form for the inner maximization problem, is to replace optimization that was trying to solve the inner maximization problem by a sampling step where we will try to sample this adversarial distribution. And why is it important and relevant? Because it leads to a very natural and practical implementation of adversarial training that consists on some slight modification of the previous method. So basically now, because we want to sample from a distribution, we need to maintain this distribution. So we kind of have this perspective tells us that we should memorize the adversarial examples that corresponds to each data point in between the step and keep them in memory as the current adversarial distribution. So this is what you have here. You initialize basically your adversarial examples. And at each time step, you load your memory of the adversarial examples. You compute your gradient or the sign of the gradient in this case to update, to basically update your adversarial examples. And you use Langevin, so you follow the gradient and add some Gaussian noise in order to kind of sample from this distribution. And then once you have this, you do your gradient descent step that are the standard update of the model against what is the adversarial data set, and you save what is very important, the attacks. So the novelty here is that instead of each time step, you recompute the adversarial example against your model, you have this adversarial distribution that you slightly update as you learn your model. And the key insight is that because we had used this entropic regularization, we have that the function, the adversarial distribution is continuous. It's a continuous function of the model parameter. So as our model trains, our adversarial distribution slightly changes, and so we can do these alternated steps in order to update each other. And we save a lot of time because now we only need 1 or 2 inner steps of Langevin instead of like 20 or 30 in practice to update our adversarial examples. So, I mean, all this wouldn't be interesting if it doesn't work in practice. So fingers are crossed. We have the first experiments that are on MNIST. So y-axis is I think the adversarial error rate. Yes. It's so error rate is adversarial test error versus PGD14. So on the test set, we compute adversarial examples and we look at the robustness of the classifier. So lower is better. And so what we see is that, of course, because we do less step of the inner problem, it takes a bit of time to take off for the learning of the model. But at the end of the day, this is faster than PGD14. But what I didn't take into account here, because here it's the number of epochs, is the fact that each step is significantly shorter because I only do 1 or 2 gradient steps for the Langevin instead of 20 or 30. So if I look actually at the time comparison, what I get is a like basically X30 faster improvement because each inner step is like basically 1 gradient step instead of 50. And so at the end of the day, we get a significant improvement in terms of performance. And this scales up also to CIFAR, where we get like 10 times faster improvement to get the performance of the standard training against PGD14. And yes.
The y-axis?
Sorry, the y-axis is the adversarial test error against PGD14.
PGD?
So, projected gradient descent, gradient ascent, sorry, 14.
So does it change if you use, for example, PGD 200?
200, I never use this one.
No, for evaluation.
For evaluation, yeah, of course, not for training. That's a good point. I should check.
It usually changes the behavior. So for evaluation, it is better to use at least 100 steps.
Okay, so this is noted. I think we can definitely do it. So what I can tell you is we were doing fast sign gradient method before, and it was even more in our favor, the results. So we will try a PGD 100. But okay, so the conclusion for the part 2 is that we have provided this distributional robustness on adversarial training by defining what is the right distributional robustness constraint in order to formulate it as to formulate adversarial training as distributional robustness. With the anthropic regularization, we got a closed form for the basically this min-max problem, for the inner maximization of the min-max problem that allowed us to replace the inner optimization by sampling. And basically the 2 tricks is basically now we have to maintain an adversarial data set that kind of warm start the sampling because this adversarial data set is a continuous function of the classifier. And we got a huge speed up. Of course, there is 2 main caveats to this method. First, we need to keep a adversarial dataset in memory, so we need to maintain it, so it's more expensive. But at least in the case of CIFAR and MNIST, it's not a problem. And even in the case of ImageNet, we are like working on some tricks to make it work, and it should. At least we should have something that fits in memory. I don't know if it's like will train well, but we should be able to have some proxy for the adversarial dataset. And the second caveat is it's an interesting one because it opens some questions, which is like it's hard to deal with data augmentation because now you cannot maintain a adversarial example for the augmented example. You don't know. I mean, you don't know in the future how your example will be augmented, basically. So you have to figure out some tricks. But I want to point out that if you look at like the standard adversarial training methods on CIFAR, it was trained with no data augmentation. It seems that using the preliminary experiment we do seems to indicate that data augmentation improved the clean test error, but doesn't improve that much the test error against adversarial examples. So that's it for me. Thank you, everyone. And I will now welcome your questions.
Questions for Gauthier?
I'll ask you a question.
I have a question on the second part. I think the distribution, like taking out the distribution to Washington, that is pretty straightforward. But why do you gain anything using the entropy regularization? Because when you add entropy regularization, before you have a coupling, right, between your x and x primes, it's a deterministic coupling. These are your adversarial examples and clean examples. But when you add entropy regularization, basically, no, you don't have a one-to-one mapping, right? So because you are increasing the entropy to get the closed form. So basically one sample, basically one clean sample can potentially be coupled to its adversarial example, maybe some other example. Right? So what's the intuition that it should help?
That's a very good question. So at least I have a theoretical intuition. We are currently investigating, doing an ablation study, whether or not it works, like it really helps in practice. But in theory, I think the good intuition is really the fact, it's what I put here, is the fact that now the distribution is a continuous function of the classifier F. And so while we are training F, the distribution is like slightly shifting to, so for instance, if you have an adversarial example before the regularization, what you have is like an adversarial example could be in a given corner. And while your function will change, like in a discontinuous way, the best adversarial example should be in another part of the space. But with the entropic regularization, at the discontinuity point, basically we would have now a uniform, they would be like as much weighted in the distribution. And so we're gonna more smoothly go from one to the other. So it kind of allows basically it kind of justify the fact that if we maintain and warm start the data set with the previously stored examples, they should the next one should be close to the previous one, so we don't need to do like a lot of steps. Actually, we can prove it. It's continuous with respect to, I think, with the KL, we can prove it.
So I have one question on this slide. So, so in so from lines, it's hard, like too many symbols, but like in line 6 to wherever, 11, 12. So where you do the Langevin, so are you touching every picture?
No, yeah, we are just touching a mini batch.
Excuse me, a mini batch.
Yeah,
but like doesn't that mean that kind of like, some pictures are like in some older, like they have not evolved enough.
Yes.
And so like, is that a problem? Or
I
like,
agree.
Yeah.
So I theoretically or practically? Practically, it's not a problem. We know, we run the algorithm. The point is, if your mini batch size is large enough, you have gone through. You have gone through the whole data set in not that many iteration. If you look at the experiment for adversarial training, I think you have a very relevant point if we were doing only 1 or 10 passes over the data. But in adversarial training, at least in the context of MNIST and CIFAR, like MNIST, we do 100 epochs. And actually we do, I stopped the computations, but like you can go way further. You can go up to like hundreds of epochs. And so it becomes less irrelevant because we really have we have passed through all these stored data points like a large number of times. But that's a very fair point that, for instance, in ImageNet, maybe it won't work that well because we may not be able to do hundreds of epochs. Though there is maybe some tricks to consider. Like for instance, we could use adversarial examples for each, like for some images that are close, and like use this one for all the images. So like kind of cluster like the representative adversarial examples in order to make a pass over it several times during the training.
I mean, presumably, the same issue. So, kind of like the question you asked about, incorporating transformations is related to that, right? Because kind of like
you never see the exact same examples, for instance.
Yeah, like you may not see the same exactly. So,
but so what you can do in that case is like having, so there is a lot of data augmentation for which you can backpropagate through it. So you could have an adversarial example on the image before doing the transformation, and computing the adversarial examples and adding like the data, basically the augmentation as a sort of like new layer.
Okay, yeah, that makes sense.
So there is a trick for this one, but I agree that for very large data sets, it's a bit, yeah, maybe we can try to kind of cluster the images. But yeah, that's work in progress to scale up to ImageNet and even larger data sets.
Thank you. Any further questions? All right, so see you again. Wait, when are we starting? In 10 minutes? Oh, I see. Okay. All right. See you in 10 minutes. Thanks again.